Hello everyone, welcome to the class. Today I will be solving the assignment for week 2 of the course Bonds and Bands in Solids. Let me share the screen with you people. I hope you can see that. So this in this class also we have multiple choice questions, and the first question says that the atoms in a one-dimensional solid are arranged along the x-axis, right? And which of the following is true for px and pz bands of the system? So let us consider a general axis. Let me draw it this way and name it as x-axis. And atoms, let's say in a one-dimensional chain, are present at so and so positions, and this is a long chain extending in both positive and negative direction. And now let us consider a scenario for first scenario for a px band. Okay, in fact, let me write the px band on the top. Now we are discussing what happens when px band overlaps for a one-dimensional chain. Now at the atom at position number 1, 2, 3, 4 and 5 and so on, this will be the orientation of px orbital of these atoms, okay, and so on in this positive x direction. And let me also put a condition that I am focusing myself on k is equal to 0 state. Now for k is equal to 0 state, there is no change in the orientation of these orbitals. I'm taking a different color here, so plus minus, I think this color might not be visible to you. Let me change it to some blue. I hope it's fine. Yeah, plus minus, plus minus, plus minus, plus minus, plus minus, and so on. Okay, and let us also take another scenario of when k is equal to pi by a for the same chain of atoms. Atoms are present at these positions. Fine. Now for k is equal to pi by a, we have plus minus for the first orbital, but the second orbital comes, it gives flipping, so it becomes minus plus, then plus minus, minus plus. Now what interesting can be seen here in this scenario is we have an anti-bonding overlap at the atom between atom 1 and atom 2, again an anti-bonding overlap between 2 and 3, between 3 and 4, 4 and 5. So at k is equal to 0, let me say for px band, at k is equal to 0, we have sigma type anti-bonding state, and at k is equal to pi by a, we have bonding interaction between, say this is atom 1, 2, 3 and 4 and so on. We have bonding interaction between 1 and 2, bonding between 2 and 3, bonding between 3 and 4. So at k is equal to pi by a, we have sigma type bonding interaction. Now if I try to plot this in a diagram, let's say this is energy, and here we have k going on. K is equal to 0 at some point. Let's say k is equal to pi by a, and k is equal to minus pi by a. Now at k is equal to pi by a, for a px band we have a minima. Let's say this is the minima at both ends, and it goes through a maxima at 0, and this is our EK dispersion diagram for a px band. Now what happens for pz band is the following. Okay, for pz band we have This is the chain going on, atoms present at so and so positions. Now if this is x-axis, z-axis would be perpendicular to it, so orbital's orientation would be perpendicular to the axis. Right, now if I consider k is equal to 0 state here, then the sign of these orbitals will not change, plus minus, plus minus, plus minus, plus minus, plus minus. And so for a k is equal to 0 state, we have bonding, and in fact pi type bonding at k is equal to 0 state. For k is equal to pi by a, these are atomic positions, we have plus minus. Now k is equal to pi by a, shifting occurs, minus plus, plus minus, because k is equal to pi by a corresponds to the anti-bonding state, pi by a minus plus. So what we have here are the anti-bonding interactions between these loops. We have pi type anti-bonding interaction at k is equal to pi by a. Now if I try to plot Ek for pz band, this is 0 at pi by a and minus of pi by a. Pz band has a bonding interaction at k is equal to 0, or I would say that energy would be minimum, and pi type anti-bonding interaction pi by a, so energy would be large. So it goes through a reverse order. At k is equal to 0, it has a minima, and at k equal to pi by a, the dispersion diagram is reversed as compared to px. Now if I plot both in the same plot, what we see, let me plot them in the same chart. Energy k 0 pi by a and minus of pi by a. Let's say that green color. For px, it goes through like this. For px, and for pz is the opposite. Okay, this is for pz. Now what do we have here in this diagram is the first option says that both px and pz have maxima at k equal to 0, but that is a wrong statement. Only px has a maxima at k is equal to 0, pz doesn't have it. Both px and pz have minima at k is equal to 0. This statement is also not correct. Both px and pz have maxima at pi by a, again not correct. Both px and pz have minima, not correct. Then fifth is px band has a maxima and pz band has a minima at k is equal to 0. Px band has a maxima at this point and pz band has a minima. So option number 5th is correct for this question. Now if we go for the next question, we can use now what it says, the atoms in a 1D solids are arranged along x-axis. Which of the following is false for px and pz bands for a system? Now this for this question we can use the same diagram here. So what I'll do, I'll copy it again here for you. Let me just move it around so that we have some space. So what it says is the energy gap between px and pz bands is minimum at k is equal to 0. the energy gap between px and pz band. In fact, this energy gap is maximum, not minimum. So this is a false statement here straight away. Now also, if we look upon other options, degeneracy of px and pz bands is lifted because now the potential is not spherically symmetric. It is only along the one dimension, and therefore the degeneracy of px and pz bands is lifted due to the absence of spherical symmetry. Pz band is generally lower than px band, which we have seen. The maxima of pz band is narrower, is narrower. The difference, or I should say the range of pz value, the energy values that pz band can take, is lesser than the range of energy values that px can take. So third option is also correct. Px band and pz band overlap. Yes, they overlap at some intermediate position. Pz band is inside the px band. Yes, that is also true. So our option is A. Moving on to the next question. It says that due to Peare's instability, the energy gap appears in a one-dimensional half-filled band at what point? So we have this information that in some EK diagram at pi by A and minus of pi by A, this diagram generally goes as this way, because E as a function of A is 2t cos Ka as a cosine function, increases at these points. Okay. Now if the band is half filled, let's say energy half this point, it corresponds to K values at both. This is minus of pi by 2a and this is plus pi by 2a. So energy gap appears in a one-dimensional half-filled band at K equal to pi by 2a and minus of pi by 2a. Now if we go to the reasoning of it, we just reason out it for you. What happens that now at these 2k values, so here we have k is equal to plus minus pi by 2a, and since k is intimately related to lambda, the wavelength of the light, so lambda in this case would be 4a. This 4a wavelength in the system can be imagined as follows. Let's say that these were the atoms, 1D atoms present, and lambda 4a means 4 atoms. Till 4 lattice constant we have one lambda, then we have another. So here, this is in this scenario, how can we realize this? Let's say the wave function of this traveling this wave, standing wave present in the system is of this sort: plus plus minus minus, plus plus minus minus, plus plus minus minus. This is one scenario, and this same scenario can also be thought if I shift it here. In this case here, this is also lambda is equal to 4a, then we have till this point again lambda is equal to 4a. Now what if we do a slight perturbation to the system? Let's shift one alternate and these were one-dimensional chain of, let's say, of hydrogen atoms. Okay, of hydrogen atoms. towards left. Let's shift these towards left. So what is the scenario we have? Two atoms closer together, then this two, so this pairing happens. Now just bring it this position and just slight orientation of the values. Okay, now in this scenario what we can do, two kinds of thing happen now. The plus, so let me just write it again. We have two atoms closer together, two atoms then, two atoms then, and two atoms. Here also 2, 2 and 2. Now if I consider this as number one scenario and this is second scenario where the traveling wave was standing wave was plus minus minus plus. Now let us have this first scenario here and second scenario here. Plus plus minus minus plus plus minus minus, and here we have plus minus minus plus plus minus minus plus. So what we have done here is that we have brought the bonding interaction closer in case number one, and anti-bonding, so this distance is lesser than this distance. Anti-bonding interactions have been separated apart and bonding interactions have been put closer together in case 1, whereas in case 2 it is the reverse case. That is, bonding in anti-bonding interaction brought closer together and bonding interaction at larger distance. So this two type of situation happening when you shift one atom towards left, and this it leads to pairing in the system. In such situation we have lifting of degeneracy in the system. And this degeneracy is occurred for pi by at k is equal to pi by plus or minus 2a, k is equal to plus or minus pi by 2a, because the bands were half filled. So the correct option would be k is equal to plus or minus pi by 2a. Now the question number 4th say that to observe Peale's transition or Peale's instability, same thing, in a one-dimensional chain, which of the following statement is false? Now to observe Peale's instability, as I said that there is a pairing in the system. So for that pairing to be constant, the lattice should be rigid. Lattice should not be flexible, that if in very slight perturbation can shift it towards left, and very slight perturbation again leads to vibration of the system, and that system can achieve the state towards right also, then will not be having that degeneracy lifting in the system. So lattice should be very stiff for Peale's instability. So the first option is straightforward, lattice should not be very stiff. This is a wrong statement. Other options we can also see, the strain energy required to distort the lattice is always lesser than the electronic energy gained during the distortion, because if the electronic gain, that is the energy gained by the system, is larger than the strain now occurring in the system because of the distortion, if this condition is satisfied, only and only then Peale's instability will occur. The system will double the unit cell if band is half filled. Yes, that is true. The system will triple the unit cell constant if the band is 1/3 filled. Yes, that is also true. Any partly filled band will show Peale's instability. So all the 4 options are correct, and the only first option was incorrect. Now for a two-dimensional lattice, in the question number 5 is two-dimensional lattice in the xy plane, gamma point in K space is defined as. Now by convention, gamma point is a highly symmetric point, and in two-dimensional K space we have kx value to be 0 and ky value to be 0. So if a high symmetry point given by kx equal to 0, ky is equal to 0, then that point is known as gamma point. So we have option 4 here. The energy at gamma, delta and x point in the K space for the S band of a two-dimensional solid in xy plane is rated as. Now for the first, let me tell what gamma, delta and x point mean. Gamma point, as we have seen in above question, is kx equal to 0, ky equal to 0. A delta point is the one where we have kx equal to pi by a and ky equal to pi by b if a and b are not same. X point is kx equal to 0 and or pi by a, one of the kx and ky is pi by a and 0, so let's take it this way, and 0. Okay, or these are two the same things, kx equal to 0 and ky equal to pi by b. Now if we take s orbitals in a two-dimensional solid, what we have is the following. These are the s orbitals arranged in the plane of the screen that you are seeing now. Now let's say for the case kx equal to 0 and ky equal to 0, we'll be having bonding interaction in the and let me mention this as the x-axis and the vertical is y-axis. So we have bonding is plus, other one also plus, 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 all in the interactions are positive. So we have giant molecular orbital having bonding interaction. Let's consider the scenario where so this kx equal to 0 was the gamma point. Now let us take x point. For x point, kx was pi by a and ky equal to 0. Now for x point we have is the following. This is the x direction, this is the y, here we have x. In the x direction is pi by a, so anti-bonding interaction in the x direction for s orbitals, but bonding in the y direction. So this take this here, let me put it here, plus minus plus minus plus minus, because in y direction we have ky equal to 0, so all the interactions will be bonding. So here we have anti-bonding in x but bonding interaction in y direction. So clearly energy in case of x configuration of kx equal to ky and at x point will definitely be greater than E gamma, right? Because we have extremely stable bonding orbital. At delta point, where kx equal to ky both pi by a, let's consider the x and y direction as same. Now here in both x and y direction we have anti-bonding interaction. Plus minus, plus minus, minus plus, minus plus, minus plus, minus plus, minus plus, minus plus, minus plus minus. And here again we have x and y. So we have anti-bonding interaction in x direction and also anti-bonding interaction in y direction. So energy at delta is very high as compared to energy at x position and energy at gamma position. So this will be the trend for s orbitals in 2D, and this trend we have for energy of x. Energy of gamma is lesser than Ex, gamma x and delta, gamma x and delta. This option is correct. Now what 7th question says is that in the similar two-dimensional solid, what would be the energies for px band at delta, gamma and x point in the K space. Now what we'll do is, rather than drawing spherical orbitals for s orbital, we'll be drawing pz bands. What pz band would do, pz orbitals are perpendicular to both x and y direction. So at these points I'm drawing the one lobe that is above the plane. At these points also, here, here and here, and these points up. Now if I'm taking again k equal to 0 scenario, we'll be having plus 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 plus, and in the bottom half we'll be having minus. So again a giant molecular orbital bonding interaction at gamma configuration. Now for x point, we have x point means kx equal to pi by a and ky is equal to 0. This is x direction, this is y. So in the x direction, in this direction, we will be having anti-bonding interaction, so plus minus plus, but in the y direction we'll be having bonding, minus plus, plus minus plus. So we have anti-bonding in x and bonding in y. At delta point we have kx equal to pi by a and ky also equal to pi by a. In this scenario, this two-dimensional diagram would become, the pz bands are vertical and we have anti-bonding interaction in both x and y, plus minus plus minus plus minus plus minus and plus. So anti-bonding in x, again anti-bonding in y. So now we can safely say that energy at delta point is greater than energy at x point, which in turn greater than energy in gamma point. So correct option would be E, gamma x and delta, gamma x and delta is this thing, which is similar to what we observed in this case of S band. Now our next question is the energies of again the same thing, but for the px band of a two-dimensional solid. Now how px band would look in a two-dimensional solid? Let's say these are the atoms in this 2D solid. Px band would orient themselves in such a way. Let's get this point. And if, and this is the x direction, and if I consider the case where k is equal to 0, or kx equal to 0 and ky is equal to 0, that is, I am considering gamma point here. So we have bonding interaction in x and bonding interaction in y. In the bonding interaction means there is no flipping of the bonding by the notion I am saying here, bonding, as the wave function will not flip if we go from one atom to the other. So it is plus minus, it will maintain its plus minus in the same direction as x, plus minus, plus minus, plus minus. Again here also plus minus, 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 and plus minus. Now what we can see here is that if I take a different color, these two interactions, these interactions in the green color are sigma type anti-bonding interactions. Okay, and if I say these two interactions, like the vertical interactions, are pi type bonding interactions. So in the case of px band at gamma point, we have sigma type anti-bonding and pi type bonding. Before commenting to other points, let us see what they have, what are the kind of energies they possess. Let's say let's go at x point. X point is kx equal to pi by a and ky equal to 0. Let me draw the orbitals. Here and this is x direction and vertical is y direction. So in the x direction we have a flipping, plus minus, minus plus, plus minus, minus plus. But in the y direction wave function will have its will preserve its sign, plus minus, minus plus, plus minus, minus plus, minus, minus plus, plus minus, minus plus. So now at x point, what we have here, as we did last time, bonding, 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 bonding. Sigma type bonding along x, and again pi type bonding along y, and this was also along y, and let me just for clarification mention it along x. Okay, so it can be said that energy at x point is lesser than energy at gamma point. Right, this can be said so far we can say this. Now let us see what happened at delta point, where we have kx equal to pi by a and ky also pi by a. So we'll be having wave function flipping its sign in both x and y direction. plus minus plus minus plus minus plus minus minus plus minus plus plus minus plus plus minus plus minus plus minus plus plus minus. So at delta point we have anti-bonding along x and also anti-bonding along y. So delta point energy would be greater than Ex because now we have both kinds of anti-bonding interactions, right? And Ex would be greater than E gamma. Now why E gamma, why the energy of E gamma is less than E delta is because in E delta, in E gamma, we had pi type anti-bonding, but one of them was bonding, okay? But in case of E delta, we have both anti-bonding interactions here, okay? So the correct option would be E gamma less than X. E energy at X position in, okay, let me correct this thing. It's not the correct way. E X would be minimum, then E gamma, and then E delta. Yes. So Ex, E gamma, Ex, E gamma, E delta. So this will be correct. Fine. Then we have another question, the reciprocal lattice of the crystal of common salt. Now crystal of common salt, this information the question has provided is NaCl is FCC structure, and we know that reciprocal lattice of FCC structure is BCC structure. So the reciprocal lattice for FCC will be BCC structure. Next question says that which of the following has same lattice structure in both real space and reciprocal space. Now we know that for BCC and FCC are there, if the real lattice is, if you take as FCC, then the reciprocal will be body centered, and if you take body centered, then reciprocal will be FCC. Simple cubic here is the only lattice among SCP, also flips its nature. Simple cubic is the one where you will find that it is a self dual, and to prove the point, let me consider the simple cube for the discussion. Just fine. Let's say this has A1, A2 and A3. In the x direction, and since we have magnitude as same as A, the length of the cube, and if one constitutes the reciprocal vector out of it, which is to say now A2 cross A3 is nothing but A square y cross z, which is x cap, and A1 Ax cap dot A2 cross A3 is again x cap. X cap dot x cap is 1, A cancels with there, and we have A square x in fact here, so we have 2 pi by A x cap. So this is a scalar quantity, and since reciprocal vector is directly in the direction of x, Okay, and this exercise we can extend to B reciprocal vector, which is to say A3 cross A1 dot A3. This will come out to be 2 pi by A y cap, and C would be A1 cross A2, A2 cross A3, 2 pi by A z cap. Now these three vectors are also in the same direction and have the same scalar factor in front of them. So a simple cubic reciprocal would be again simple cubic. Alright, moving on to our next question. The volume of a primitive unit cell and reciprocal unit cell of a face-centered cubic lattice of side AR. So first let me just quickly draw a face-centered cell. Atoms are present at these locations, at corners and also at the face center of the cube. And let's say this is the center from where you can draw these. Now for an FCC, the construction of primitive vectors is done as the following. Let me choose this as 0 0 0. This would become A 0 0 0 if I take this direction as the x-axis, y-axis and z-axis. This would count to 0 A 0. This would become A and 0. Fine. So if I take this atom and take out this vector, take this one at the lower face and at the side one. Using these three vectors, let me call them as A equal to A by 2 x cap plus 0 y cap, A by 2 z cap. And this A vector is the one which has A and Z component to it. That is, it is going in the x direction and in the y direction, so I'm calling this as A. B vector as A by 2 x cap plus A by 2 y cap 0 z cap. It is in the x and y, that is, this is B. C as 0x A by 2 y plus A by 2 z cap, and this will be C. Now using these three primitive vectors out of an FCC, we can find out the volume of this primitive. Since we have to find the primitive unit cell, we have to find the primitive unit cell. We have done that. So volume is nothing but the scalar triple product of the primitive unit cell is A dot B cross C. And if one carries out the cross product of B cross C and take a dot product with A, we find the value to be A cube by 4. Alright, and if one constructs the reciprocal vectors out of it, A, B, C are our primitive lattice vector, and let's say I give the name to reciprocal lattice vector out of A, B and C. Let's say I give it U. U will be 2 pi B cross C divided by A dot B cross C. Okay, now let us try to find out what U is. U is 2 pi. B cross C would let's find out first. Let's find out what B cross C is. Would be determinant of B and C, which is A by 2, 0, and C is 0, A by 2, A by 2. B cross C comes out to be x cap A squared by 4 minus y cap A squared by 4 and plus z cap A squared by 4. Okay, and if we find this B cross C we have found out, so taking a dot product with A would give us A. We already have A0 A by 2, so A by 2 x cap plus 0 y cap plus A by 2 z cap is A. So now we are finding A dot B cross C, that is the volume. Dot product with x x of A squared by 4 minus y cap squared by 4 plus z cap A squared by 4 fine. This is our B cross C. Just let me check again. B cross C yes, let me just think a bit. Volume we have found out B cross C to be A cube by 4, that is okay. Then we constructed these vectors. B cross C we have found out to be this. Now A dot B cross C would be A cube by 4. Okay, yeah, okay, cool. That we have done. In fact, A dot B cross C, if we do it, be A cube by 8 plus A cube by 8 is equal to A cube by 4, which we already did previously, which I skipped as is an easy exercise. Now if we divide this U, as I said, 2 pi B cross C divided by A cube by 4, which you have just found out. 4 goes above, becomes 8 pi by A cube B cross C we have in front of us, and the A square by 4 factor comes out x cap minus y cap plus z cap. Okay, so for 2 we have 2 pi by a x minus y plus z here. Let me do this. So first vector we have found out, our reciprocal vector is this. Okay, now by analogy, if we try to extend it, 2 pi by a, now in u y is negative, in v z will be negative, and if I say w here, 2 pi by a, then x will be negative. Now we have these 3 vectors with us. Volume of these vectors will be this. Now let us find out. V cross w is 4 pi square by a square x, y and z. We have 1, 1, minus 1, minus 1, 1, 1. If we expand it, for x it comes out to be 2. Okay, and then for y it is comes out to be negative plus z plus 1. We are having 2 of z here, and y has become negative. V cross w, fine. Let me just check a bit. B1, it should become in the way B2 was this, and okay, let us do it. 2 of x we have, then 2 of z we have here. Let's try to continue what happens then. We'll see. 1 plus 1, 2. We have 1 minus outside, 1 minus 1. Let's see how we end up. And u is 2 pi. Now if we take a dot product with u dot v cross w would become 2 pi by a x minus y plus z dot 8 pi square by a square x plus z. So it becomes 8 16 pi cube by a cube. X into x becomes 1, z, y is 0, z into z is 1. So we have 32 pi cube by a cube. It was a bit lengthier derivation to do, but anyway at the end we have got our conclusion as 32 pi a cube pi cube by a cube as the volume of the reciprocal unit cell, and a cube by 4 as the volume of the primitive unit cell. If you go up, so this option we have for the primitive we had a cube by 4, and for the reciprocal, so option 4 is correct, 32 pi cube by a cube. Now the next question is, if a, b and c are primitive lattice vectors in the direct space, and a, capital B and capital C are corresponding reciprocal lattice vector in the reciprocal space. Now what do we have here? So A in this scenario would be defined as B cross C by A dot B cross C. Now a cross product, the resultant of a cross product is perpendicular to both of the vectors. So B cross C, the resultant is perpendicular to both B and C, right? So if A, B and C are primitive vector, A is not perpendicular to A. Capital A is not perpendicular to A. Yes, because A is in direction of in fact A, capital A is in direction of A. Then capital A is not perpendicular to B, but is perpendicular to B but not to C. No, this is not correct. A is not perpendicular to A. This statement was right because it is parallel. A is perpendicular to B but not to C. Wrong. Then B is perpendicular to both A and C. Now one has to find out what B is. As we know, is C cross A dot B cross C. B is perpendicular to both A and C. Yes, B is in fact parallel to the plane defined by C and A. So this is also right statement. D is A is perpendicular to A. Wrong. So E says both A and C are correct. A and C. So correct option is for the 12th is both A and C. Then we have the next question as boundary plane of a Brillouin zone satisfy the condition. Now let's satisfy the condition. Which condition it is, A, B or C, where K of capital Kn is the reciprocal translational vector and K is a vector in the reciprocal space. Now how do we go about it? Let us take an example of a 2D lattice. Okay, and we have our vector, let's say coming from point A to some point O. This is the incident vector. Let me denote it as K, the vector in the reciprocal space, and there exists a Kn vector. This is a Kn vector which is a reciprocal lattice translational vector, and let's say this another vector in this direction to be K prime, right? So according to the law of vector summation, we can write small k plus capital Kn is equal to K prime. The vector goes in this direction and then in this, and the resultant is given by K prime. So if you take square both sides of this vector, one can write k mod square kn vector mod square plus 2 times k vector mod dot twice of k vector dot kn vector is equal to k prime mod square. Now k and k prime are actually the same. The magnitude of the k and k prime is same, because if one forms because k and k prime are connected to lambda, and both are 2 pi by lambda in the sense. So if one forms a evolved sphere out of this, if I try to prepare a sphere, then the magnitude of k square and k prime both are same and can be cancelled out. So we have the condition kn square plus twice of k dot kn is equal to 0. So twice of k dot kn, this is the right option. Okay, but also in this situation one can also write this law of vector summation as if I do like this, and let me treat this as O A and this point as B, O A B. So O A to O, this is, we have k vector, A to B we have kn. Okay, but O to B, sorry, A to B we had k prime, but O to B is kn. Now I can also say that this goes in the opposite way, right? In that situation I would have k vector, k prime vector plus kn equal to k, and bit of rearrangement would give me k minus kn is equal to k prime. And if we do the same thing, summation both side, k prime, k vector mod plus kn vector mod square minus of small k dot kn is equal to k prime mod square. Again, k square and k prime mod square are magnitude are same. We are left with the condition is equal to 2k kn. This is also similar condition as we have found here. So option C is also correct. Okay, A and C both are correct, so therefore correct option for this question would be D. Now the question 14th says that the basis vector of a three-dimensional lattice are given as A to be 2x, B as x plus 2y, and C as z. The corresponding basis vector A, B, and C of the reciprocal space are: A is 2 pi B cross C divided by A dot B cross C, and as this follows. So B cross C we can find out from a determinant x, y, and z as 1 B cross C we have 1, 2 and 0, and C would be 0, 0 and 1, and if you expand it, it comes out to be 2 minus y plus 0 z. So 2x minus y plus 0 z cap, and A dot B cross C, that is dot product with A, become 4, because 2 here, here and 2 here would give a dot product, and A dot B cross C would be 4. So capital A 2 pi into b cross c we just found out, 2x cap minus y cap divided by 4 becomes 2. If I take an additional page here, if you go on the next page, a becomes pi x cap minus pi by 2 y cap. So a is pi x cap minus pi by 2 y cap. So here we have one option of only of this kind. In the similar way we can also find b reciprocal vector and also c reciprocal vector, and if we do that, b would come out to be pi y and c come out to be pi z, because in this question we can use the option rejection technique. Since we have found one of the reciprocal vectors correct and all of the other options are different kind, we can safely say that the right option is A. So now the final question for the present module is, if the primitive translation vectors of a conventional lattice are a1 ax, a2 ay, and a3 az, the volume of the primitive cell of the reciprocal lattice is. So now we know that volume of reciprocal space having vectors a comma b comma c is equal to a dot b cross c, right? And in this thing we can find a as 2 pi a2, in fact let me write it more clearly, 2 pi a2 cross a3 divided by a1 dot a2 cross a3. If we do that, 2 pi divided by a1, now a2 cross a3, a2 cross a3 would be a square, y cross z is again x cap, divided by a square x cap taken dot product with ax. We are remaining with 2 pi by a x cap. In the similar way we can find out b as 2 pi by a y cap and c 2 pi by a z cap. So a dot b cross c, that is the volume of the reciprocal unit cell, would become 2 pi by a x cap taken dot product with 2 pi by a y cap cross product of 2 pi by a z cap. We have 8 pi cube outside divided by a cube into x dot y cross z is 1. Here we have volume of reciprocal unit cell, and this down is nothing but volume of real unit cell, okay, RL. DL is the direct lattice or the real lattice, and RL is the reciprocal lattice. And if we go back, so V of reciprocal unit cell is VRL, V of real unit cell or direct lattice, we can be said it is a multiplication sign, not a direct, not a cross product, is VTL is equal to 8 pi cube. So 8 pi cube above in the question is our correct answer. So in this way today we have solved our second module or second assignment for the week 2. So with this I would end this following session. We'll meet you in next week. Bye.